Hello, uh, welcome to IWSS 2020. I'm Janaka Adissuryaa. My title of the presentation is Asteroseismology of Delta Scuti stars. So I'm working as a research scientist at the Astronomy Division of the C Clarke Institute, Sri Lanka. So let me proceed my presentation. So this is the overview of my presentation. So I would like to discuss about the brief introduction about asteroseismology. What is asteroseismology? Just to give some idea about what is that. And this asteroseismology can be applied to different type of stars, but I just select about Delta Scuti type stars. This is a particular type of variable stars, so I'm focusing on that. So just give some idea about what is Delta Scuti star, and then so determination of pulsation frequencies. So this is based on the pulsation or the oscillations of stars. So I will explain about how do you find out the pulsation frequencies, and a case study. So that means one example I will show you how this asteroseismology applied on variable stars or the pulsation stars based on this example. That is, the particular star I selected here is SERF, what I observed. And then finally the oscillations modes, they are in the SERF. So how do you define, how do you determine the oscillation mode of SERF? And finally the application of this asteroseismology is to find out the properties of these pulsation stars. So I will just look at these areas in my presentation. So let me go to the next slide. So if we want to get some brief idea about what is asteroseismology. So it is the concept of asteroseismology is a long time back. Actually, it's a kind of quite new for astronomy, and this is just idea of listen to the stars rather than looking to the stars. So we can say that is listening to the stars. So why is it? Because this is based on some sort of the pressure waves or the sound waves just created inside the star, so that the pressure waves or the sound waves actually just generate some physical changes of the stars. Basically, it's a change of magnitude or the brightness. So however, by looking at these magnitude or the brightness variations carefully, we can investigate the inside the stars. So that's why we call this is rather than looking to the stars, we call this is listening to the stars. Now we know the asteroseismology is a real music of spheres, because the spheres actually just make these oscillations or the sound waves inside that, and these sound waves create some changes, surface changes of the stars. So once you look at these surface changes, so we can analyze in detail about the internal structure of the star. So that is the asteroseismology. So this is the only way to probe the inside the star, right? So there are different pulsation modes penetrate in different depths inside the star. Therefore, we can investigate the different depths of these stars. So that is another important advantage of this asteroseismology. So all the way from the surface to the core, if you want to look at it in detail, this is the only way to study. Asteroseismology provides a tool to find the internal structure of the star. The pulsation frequencies give information about the density profiles, temperature profiles, region where we just looking at it in detail, where there's no other way of studying about this internal structure. So that is the idea about this asteroseismology. Okay, so here the brief introduction about this, how it's going on here. If you look at the interior of the star, so these are the pressure waves or the sound waves, right? Just move in different layers on different depths inside the star. These are the standing wave patterns created. So if you look at this blue line, so that standing wave or the pressure or the sound wave travels through the center of the star. But if you look at this red standing wave, sound wave, it just move within the surface or close to the surface, the star. So if you detect these frequencies of these oscillations, you can determine the different depths of the star, you can determine the properties, or you can determine the internal structure within the star. So you can actually see here these vibrations or the standing wave patterns create different the surface brightnesses. So in the color here, this is maybe a contraction, this is maybe expansion. So therefore, in one part is in compression, and another part of the star might be expansion. So therefore, there's some sort of a combination of expansion and contraction along the surface will give a very good idea, a good tool to analyze the star inside the star. Okay, right. So here, so that is basically about what we call asteroseismology, and here I will apply this tool, the asteroseismology, to particular type of star, because we have a set of variable stars, intrinsic and extrinsic. So I'm just looking at this part only, intrinsic variable stars. So from the intrinsic variable stars, there are a lot of other type of intrinsic variables like RR Lyrae, beta Shepherds, supernovas. So among those, I just select this delta Scuti type stars only. There's one reason that these delta Scuti type stars are very short period variables, which we can actually get the variation within 1 day. So in the observational constraints, so it is very easy to get few cycles within 1 night. If you look at the RR Lyrae, so the variation or the periodic variations are more than 1 day, the periods. So therefore, if you want to observe a few cycles, you have to continuously looking at it for a few nights of observation, or if you have to get a very big data set to get some idea. So that is the one advantage of just going for delta Scuti stars. So then I just pick these delta Scuti stars for my study. So just show where these different type of variable stars in the HR diagram. So if you look at now, this is the main sequence, right? And there are the most stars actually lie on the main sequence before they actually just end up their life cycle. So some of these main sequence stars just move it to the other areas. So most of the stars actually move it from the main sequence. They become, most of them sometimes become variable. Of course, if they become a red giant, that is a variable, because they are not going to be same as earlier at the main sequence. So here, when they just move it from the main sequence, so they will start changing their brightness. So it's quite often they are variable. So the delta Scuti stars are in this area. This is called the instability strip. So just above this main sequence, just after the main sequence, they just move into this area, what you call the delta Scuti stars. So the RR Lyrae is somewhere here. Then the Shepherds are in this instability strip, and here the supergiants, and the beta Shepherds are very big stars, huge stars, somewhere here in the HR diagram. So I'm just focusing on this area, what we call the delta Scuti stars. Okay. So this is some sort of overview of all the variable stars, right? If you look at different variable stars, RR Lyrae, Delta Scuti, Beta Cepheids, this is a rough estimation about the periods. RR Lyrae, it's quite big periodic stars. The periods are more than 1 day. Delta Scuti, look at that. So it is 1 to 3 hours, or it's very small periodic change. So it's just quickly changing stars, right? And they are mostly population 1 stars, right? Delta Scuti, quite new. More metal abundance, heavy element abundance is there in Delta Scuti. And Delta Scuti and the Beta Cepheids, both of them shows radial and non-radial pulsations. So let me show you in the next few slides what are radial and non-radial pulsations. So this is the just a general idea about all the stars, variable stars, pulsating stars. Okay, so here the Delta Scuti, furthermore, I just move it some parameters of Delta Scuti stars. They are population 1, high metallicity, relatively young stars. The mass range is 1.5 to 2.5 solar masses. That is the typical range of Delta Scuti stars. High amplitude variation. I mean, the variation of the magnitude variation is very much. It's in the magnitude scale, some of these stars, 0.3 magnitudes. So it's very easy to identify these magnitude variation with a small telescope. And the pulsation period is less than 1 day. The rotation, typically it's slow rotators. It's a 30 meters per second rotation period, V-cyanide, right? And they are in the central hydrogen or shell hydrogen burning. This is very important. Central hydrogen or shell hydrogen burning. They are just leave it from the main sequence. So the core hydrogen is almost finished. So they are moving to the shell hydrogen burning state. That's why it's very important to study about this particular type of stars. Then they have convective core. So with this, we can actually see that how important is studying about these Delta Scuti type stars. Okay, so now this is about the 3D oscillation, how it happens inside the star, very briefly. Radial oscillations. Now these pulsations, sometimes it makes standing wave patterns. So if you look at a standing wave, this is when you make a standing wave, always the center is a node and the surface is an antinode. So therefore this is the most basic standing wave pattern. And then you can see the next standing wave pattern. There's a one shell, the layer, where there is one possibility of making another node. This is definitely antinode. So these are radial standing wave patterns. But if you look at this, right, this diagram, they are non-radial standing wave patterns. So therefore, we have a radial and non-radial oscillations. So if you look at these two characteristics, stars actually oscillate in radial and non-radial both oscillation modes. Now when we define these oscillations, we need 3 numbers. They are very important, like quantum numbers. So we call this quantum numbers. N is the number of radial modes. L is the degree of the mode. That means L is just to define the non-radial oscillations. M is also to define the non-radial oscillations. So I cannot actually go in detail about these things within this limited time. But remember, N is the radial modes. L and M are the non-radial oscillation modes. So so this is the idea about the non-radial oscillations. So if you always look at L equals 1, that means that is the start of non-radial oscillations, non-radial components. So L equals 1, M equals 0. Then there are a lot of combination like L equals 1, M equals 1, like that. So you can see the star oscillates in a very complex manner with these combinations. So that's what we are looking for. So first of all, when we are looking about the asteroseismology, we have to determine these oscillation modes, N, L, M. So even the mode, whether it is L equals 1 or L equals 2 mode, right? So that is very difficult in the first case. So that's what we are supposed to do here. So this is a radial oscillation and this is an unradial oscillation. So it is not symmetric, right? Here. And this is the light curve. Now we have only a one tool, right? We have only a one way of determining all these oscillation mode, that is the light curve. So if you look at the pulsation light curve of a pulsation star, so the light curve is sometimes very simple, sometimes it's very complex. Now even if you look at this light curve, this is you can see a very common, very prominent oscillation here. Of course that is a main oscillation, but when you look at carefully, there are some slight bounce off from the light curve. So that means within the main oscillation, there are some small oscillations as well. This is the main oscillation. Within that main oscillation, there's another oscillations going on under that. So therefore, when you look at this light curve, there are some other bumps also, some other characteristics you can find out. First of all, we have to find out how many frequencies are there within this light curve. So in order to do that, we have to go for the frequency analysis of the light curve. So there are different techniques we can apply. Fourier transformation is possible, the most common. Long-scale periodograms we can calculate. Structure function analysis or maybe phase dispersion minimization techniques can be applied. So here I did my observation of this particular star called SEZ Lin, that is a delta Scuti type stars. I did my observation using Mount Abu Observatory in India. So let me thank about the facility from India. So I use this telescope in Mount Abu Observatory, 50 centimeter CDK telescope. This is a very handy telescope with all the facilities, which is equipped with the UV-VRI filter wheel and then the CCD, EMCCD. So this is a very handy telescope to observe this particular type of stars, short period stars, because we can actually observe throughout the day without any interference. This is a robotic telescope. Even we can actually observe, we can operate it from main campus PRL. So I use this facility for my observation. Right, so this is the light curve, which we part of a light curve I actually obtained from Mount Abu Observatory. Right, so this is the first this is the observation of Mount Abu Observatory. I just compare this observation with another facility. This is called Wide Angle Searching for Planets, WASP project. This project is actually going on to investigate exoplanet systems, but this project also observed the Z-Lin, so I just got that data set as well, and there are some data available in AVVSO site as well. So I just got this Z-Lin from the AVVSO as well. But when you look at these three observations, now we sampled our data set within 3 seconds. So that means UV-VRI observation was done within 3 seconds. I mean, we have a very high time resolution photometry. But if you look at the WASP, that is a 1 minute resolution. So AVV is 4 minute resolution. You can see how important is our light curve. So you can see this is very detailed. So it's a very high resolution light curve, temporal resolution. So we can actually use this one to detect all the frequencies, even a very short high frequencies within this light curve. Right. So this is the part of a light curve, and in BVR bands, you can see the BVR bands. I put it together, and here I just normalize to the maximum point. So here, of course, by just looking at even without just analyzing the light curve, I can actually see some other frequencies available. Here are the other variations. Of course, there's a main variation, main period frequency F0, and there are some other variation like F1, F2. So let me show you the results of the frequency determination of using these light curves. That means we have, when you just look at the light curve in detail, when you do the Fourier decomposition of the light curve. So this is the main light curve. So you can see the same shape. And when you decompose it to find out the frequencies within the light curve, you can see the main period, main frequency in red, and there are some other frequencies in green and the blue, as well as some other minor frequencies also there in this light curve. So this is the Fourier decomposition of the light curve of acetylene. So let me show you the next slide, the results of this. Okay, now when you do the frequency analysis using DFT, Fourier transformation, or I rather use Lomskagel, LS method, Lomskagel periodic analysis. So this is the periodograms. So this is the periodigram of the acetylene light curve. We can see clearly here the one frequency is exactly it's there. This is the most prominent frequency we observed it. Of course, this is very small, but that is 8.296 cycles per day. This is the most prominent frequency in that light curve. So then after that, we detect another frequency, that is 16.59 cycles per day, and then furthermore we have more frequencies in that light curve. This is the Mount Tabu data. This is another observation I contributed with the ATP telescope in Arizona. So that telescope also observed the same target as acetylene. So here with that data also we can see the same frequencies we can determine: 8.296, 16.2959, and then 24.89. So the same frequencies will get it from other sources also. That means this star has different frequencies in its light curve. So this is another important thing I wanted to show, that actually so since this presentation it's just run it on some other way, we have to eliminate. Now this is the first frequency, that means the most prominent frequency. In order to observe the other frequencies very clearly, we have to eliminate this main frequency, what we call the whitening. So I just did the whitening of the first frequency. So then I look at the next frequencies, because if you don't do this whitening process, because the dominant frequency will affect the other frequency, and you don't get the other frequencies very clearly. You don't detect it very clearly. So therefore, the whitening process is important. So I just did the whitening of this 8.296 frequency, and then only you can determine, you can clearly see the others are actually come up in the light periodigram. So the whitening process is very important. Okay? So after all these analysis, so I just move it to this. This is another way of removing the harmonics. So if you have the main period, so you can actually determine the main period and remove it from that. So then you can look at it, the rest of the frequencies within the residual light curve, right? So this process is very important, because otherwise you cannot determine the hidden frequencies, very weak frequencies within the light curve. So this is very important, this analysis process. So after all this, now this is actually these two frequencies are frequency aliasing, artificial frequencies. In order to remove this, we have to do the whitening process. So after all this, I determine the pulsation frequencies of acetylene, and then I figure it out. There are there are 9 frequencies we determine from the Mount Abu data, and the WASP project we can determine up to 5 frequencies, because you know the time resolution is very low, and ABVS also determine up to 5 or 6 frequencies, but I determine up to 9 frequencies from Mount Abu data. So these are the frequencies which I determine, the power spectrum of the frequencies. So first of all, we have to determine the frequencies of the pulsation star. Then we have to analyze what is the mode of these frequencies, whether these frequencies are radial or non-radial, and if it is a non-radial, what is the mode, whether it is L equals 1 or L equals 2. For that, we have to go for another detailed analysis that is called the oscillation modes, right? Determine the oscillation modes. So in that case, we have to determine the amplitude of these oscillations. Now you can see the main frequency, the amplitude of the main frequencies are this. For B band, this is the amplitude. For B band, the amplitude, and the R band. Now they are not same, right? They are not same. So if you look at the first frequency, that means the frequency of this 8.297, this is the main frequency. That frequency, the amplitude of that frequency in the B band is 0.7, and B band is 0.5, R band is 0.4. So they are different. We have to determine these amplitudes later on. So once you get the amplitude of these frequencies, these are the amplitude for first frequency and the second frequency, third frequency, we get the amplitudes and the phases of these frequencies. Then we have to determine the amplitude ratios, right? Amplitude ratios of the B band, amplitude ratios of the B band and the R band. So once you get the amplitude ratios, then only we can determine the modes of these oscillations. So therefore, we have to go for in a very detailed analysis of theoretical modeling. Now we have to model these amplitudes artificially, theoretically. So in that sense, we have to go for very detailed analysis of theoretical analysis. I don't want to actually show all these stuff in this short presentation, but you can find out these theoretical amplitude determination from the literature. So once you do the theoretical amplitude calculation, then you can compare with the observation. Now in the theoretical modeling, right, the theoretical modeling is the most complex part of this research, because it depends on so many factors: temperature, gravity, mass, metal abundance. All these have to take into account, right? Because all these factors determine the theoretical amplitude of these oscillations. So therefore, all these are the inputs to determine the theoretical amplitude. So we have to input to our model all these variations and then see whether these theoretical amplitudes are matched with the observed amplitudes. So if it is not converging, we have to go back, and then we have to change again the parameters and then see whether this is approaching to our observations. So this process is very complex. You have to do it again and again, very time consuming process. So however, when you do this, finally we can have some sort of a results, acceptable results with the desired temperature, gravity and mass parameters. So then once you do this thing, not only you are converging to the observation, but also you are determining the parameters of your star. Of course, let's say you are not certain about the parameters of the SZ lane, that is which I actually use it here. You start with some sort of a average or maybe some initial values, but you can converge your parameters, stellar parameters, to a quite accurate values within this process. That is another advantage of this. So let me show you. These are the amplitude ratios you compare with the observation. These dots are the observations in the three bands, B, V, R bands. These are the observations. These are the theoretical lines. See that this line is L equals 0, this is L equals 1, L equals 2. So you can change the modes in the theoretical analysis, L equals 1, L equals 2, L equals 3, and see whether your observation will fall on these areas, whether it is fall on L equals 0, L equals 1 or L equals 2. So therefore, then you have a method to clearly say my frequency, the oscillation is exactly equals L equals 0 mode or L equals 1 mode. So this is the method. So then I will show my results later on. Now this is my observation. So the results of SZ lane. So I observed two frequencies. Actually I did for only two frequencies, because you know that the other frequencies are very small. It's very difficult to determine the amplitudes. So these two frequencies I can determine the amplitudes. So the frequency of 8.297 and the frequency of 16.59. And I did two models. I did my theoretical analysis based on two models. That is, one is mass is 0.2 mass, solar mass. Temperature is around this 7522 K. Log G is 3.77. These are the parameters I used for my theoretical analysis. And another model, just a 1.9 solar mass and slightly a higher temperature of 7557, and log G is 3.86. So you can see the blue line is this model and the red line is this model. So therefore, these frequencies I can match with these models as well as with the modes of the oscillations. So here the blue line is more close to the observation. Of course, I did chi-square analysis, chi-square minimization, otherwise it is very difficult to say that. But when you do the chi-square minimization of these three observations with the theoretical line, you can say that which one is close by. So here I can say here in this case this model is more appropriate. Therefore, I finally determine the temperature of SZ lane as 7557 and log G is 3.86 days. So that is my conclusion of the physical parameters. And of course, the mode of the oscillation is L equals 0. So L equals 0, because this is very close to L equals 0. The continuous line is L equals 0. So therefore, these oscillations are radial oscillations. They are not non-radial oscillations. So finally, of course, we can further study about the mass of the star. If you have these evolutionary tracks, so I use the MESA code to produce the evolutionary tracks which is close to my star. So I did the evolutionary tracks for four masses: 1.8, 1.85, 1.9, 1.95 and 2. So these are the evolutionary tracks which is close to my star, and even that evolutionary tracks actually shows that these are the two models which I use it. This model is 2 mass star and this model is 1.9 mass star. However, evolutionary tracks fall some little off from that. However, maybe if we can say that this one is very close to that, and this one is the close one from my observation. So therefore, the mass of the SZ lane would be something like 1.9 solar mass star. So I mean, this is a very long process, very complex process. So you have to go again and again. The analysis, theoretical analysis, you can modify the theoretical input parameters, and however, you have to come closer to the observation to get the physical parameters of the star, as well as you can determine the oscillation modes with this analysis. So that is all about my explanation. I hope that you might get some idea about asteroseismology and the applications of astronomy, which is very important to determine the stellar parameters. Thank you very much.